Hi, my name is Luke and I'll be presenting our paper HyperDUM, Hyperdimensional Uncertainty Quantification for Multimodal Uncertainty Fusion in Autonomous Vehicles Perception. Autonomous vehicles leverage multimodal sensors and deep learning models to detect and track objects, collect data and intelligence, identify drivable areas, and inform planning and control. However, sensor-specific limitations introduce uncertainties into perception, posing challenges for feature fusion as demonstrated in the video. How can we effectively quantify modality-specific feature uncertainty to reduce uncertainty propagation errors? Existing uncertainty works suffer from high computational costs, poor calibration, or require end-to-end training using specially designed loss functions, making them impractical for real-time autonomous vehicle systems. Can we have a lightweight, deterministic, feature-level uncertainty quantification method that works post-hoc and seamlessly integrates into any fusion framework? We propose HyperDUM, a novel hyperdimensional deterministic uncertainty method that efficiently and effectively quantifies feature-level epistemic uncertainty. Our method leverages high-dimensional encoding for efficient uncertainty estimation. We improve uncertainty quantifiability through our novel patchwise and channel-wise encoding to capture both local feature-level uncertainty and global sensor-level uncertainty. Our similarity-based uncertainty method is then used to dynamically adjust each sensor's contribution to produce uncertainty-aware fusion for improved reliability. Hyperdimensional computing can be considered a type of prototype learning. Prototype learning is defined as a cognitive process that involves learning a category prototype from a set of examples. It's based on the idea that people use the central tendency of examples to categorize new things. Take the example of recognizing images of cats and dogs. Humans can identify cats and dogs by their common and distinctive features. We can form a general concept of what typifies a cat or a dog. This general concept represents the prototypical features of a cat or a dog, i.e., pointy ears, small size versus round ears, and larger size. Now, when we see new images or ones with partially useful information, we are still able to identify features that closely resemble our knowledge. We can leverage prototype learning at the latent feature level to quantify epistemic uncertainty of a model's internal representation and its knowledge of the training data. In the AV case, during training, the prototypes are formed based on scene context such as cloudy, rainy, sunny, foggy, and night. During inference, we compare the similarity of the input sample with the existing prototypes to quantify the uncertainty of the input with what the model knows. The relation between uncertainty and feature weights are then learned via the task supervisory signal. If no context label are available, one can use clustering or other method to generate pseudo-labels for unsupervised prototype formation. We evaluate our method on the AI motive and deliver datasets, which provide diverse uncertainty scenarios including adversarial weather conditions and sensor failure cases. For 3D object detection, our method can, on average, outperform the state-of-the-art algorithms by up to 2.01%/1.27%. For semantic segmentation, our method can, on average, outperform state-of-the-art algorithms by up to 1.29%. Additionally, our method requires 2.36 times less floating point operations and up to 38.30 times less parameters than state-of-the-art algorithms. Finally, we present some qualitative results that show the improved effectiveness of our CPB plus PPB. Overall, channel-wise projection and bundling, CPB, captures coarse-grain uncertainties, while patchwise projection and bundling, PPB, captures fine-grain uncertainties. Together they improve the uncertainty quantification effectiveness, leading to improved overall robustness. To conclude, we motivated the need to quantify modality-specific feature uncertainty to reduce uncertainty propagation errors in fusion. We presented our novel hyperdimensional deterministic uncertainty method that efficiently and effectively quantifies feature-level epistemic uncertainty. We evaluate our method on the AI motive and deliver datasets which provide diverse uncertainty scenarios including adversarial weather conditions and sensor failure cases. Our evaluations show that our method can improve overall model performance as well as being more efficient compared to state-of-the-art methods. Thank you for your attention.